Hey guys, welcome to my class on binary operation, and in today's class I'm going to be talking about the closure property of binary operation and the commutative properties of binary operation. But in this class I'm going to mention all the properties of binary operation, so stay tuned. If you haven't subscribed to the channel, smash a like on this video and endeavor to click the subscribe button, and I'll see you in this video. So welcome to this class on binary operations, particularly this class on the properties of binary operation, okay? So I'm going to be mentioning all the properties of binary operations and thereafter discuss in detail the properties of closure and the properties of commutativity, okay? So let's start with mentioning them. So there are basically 6 properties of a binary operation. Number 1, the first property of a binary operation is the property of closure. Okay, so I'm going to call this closure property. Now, even when we call closure property a property on binary operation, the closure property is particularly for the non-empty set. So it is a non-empty set that is closed, not a binary operation. Binary operations are not closed. It is a non-empty set that must be closed with respect to a binary operation. So closure property is on binary operations, but it is particularly for the non-empty set. That brings me to the second property, which is the commutative property. Okay? So the commutative property is the second property on binary operations, and I'm going to be discussing that in detail in this video. And that brings me to number 3. So again, before I proceed, take note, closure property belongs to the non-empty set, commutative property belongs to the binary operation. So it will be proper of you to use the language is a binary operation commutative, but it will be wrong of you to use the language is a binary operation closed. So a binary operation cannot be closed. A non-empty set is closed or not closed with respect to a binary operation. So binary operations could be commutative, and that brings me to the next one. The next one is the associative property. So this one also belongs to the binary operation. So it is the property of binary operations but belongs particularly to the binary operation. So that brings me to number 4. Number 4 property is the property of distributivity. I'm going to call this the distributive property. Okay? Now we shall be discussing these other properties I'm mentioning in my subsequent lessons on binary operations, but I'm going to mention them nonetheless in this particular video. And that brings me to number 5. In number 5 comes the property of the identity element. So I'm going to write this as the property of the identity element. The property of the identity element. Okay? And that brings me to number 6. Number 6 is the property of the inverse element. So these are all properties on binary operations. Okay? So in this video, my focus shall be on the first and the second. So quickly, without waste of time, let us come to the first property. So what is the property of closure? What does closure property mean? Let's examine that with an example or 2. Okay? So a non-empty set, say capital S or uppercase S, is said to be closed with respect to a binary operation. With respect to a binary operation, asterisks. Remember in our last class we decided to use asterisks to represent a general binary operation and S, capital S, to represent a general non-empty set. So when is a non-empty set closed is the question we want to answer under this property. The property says a non-empty set X is said to be closed with respect to a binary operation if what happens. In this case, my binary operation is asterisk, and this will only happen for that non-empty set if and only if any 2 elements, say A, B selected from X has A asterisk B as a member of X. Now what this means is this: for this particular property, if it is possible to select from a non-empty set, remember a non-empty set is a set that contains elements. If it is possible to select from a non-empty set two randomly chosen elements, say A and B. Remember again, in our previous video we talked about elements as being numbers or algebraic entities. So if I choose two elements at random, say A and B, from a non-empty set S, this A could represent a number, the B could also represent a number, A could represent any abstract entity or algebraic entity, and so also can B represent such. Okay, so if I choose A and B from a non-empty set, and it is possible that a combination of A and B using the binary operation asterisk gives us a result in X, then and only then would you say that that non-empty set is closed. Now, if a non-empty set based on a binary operation fails this condition, then that non-empty set is said not to be closed. Okay, now let us quickly look at an example. Let us look at an example on this. Okay, I'm going to call this example 1. So let's see a first case on example 1. Is the set S containing 1, 2, 3, and 4 closed with respect to multiplication as a binary operation? The answer to this question is a point blank no. But let us see why the answer is no. This set is not closed with respect to a binary operation, and let's investigate why that is so. For you to test the property of closure as a student, all you have to do is to select any two elements from that at random from the set. In this case, the non-empty set given to us contains 1, 2, 3, and 4 as its elements. Now, if you want to test whether or not this non-empty set is closed with respect to the binary operation in this case is multiplication. If you want to test if this set is closed, all you have to do is choose any two elements from the non-empty set at random and combine them using multiplication. If the result of combining them with that binary operation gives you a result in X, then S is said to be closed. But if it is possible to have a combination, whether one combination or two combinations or more, that will give you results that are not in S, then that set is said not to be closed with respect to the binary operation. So let's check. Now, you will notice that choosing elements 1 and 2, if I choose elements 1 and 2 from S, notice that by implication, 1 multiplying 2 will give us a result 2, which is also a member of S. And if you stop at this point, you may jump into a quick conclusion that S is closed because the condition is satisfied in this case. But I'm going to tell you, using this particular set, that S is not closed. Why? If you pick 3 and 4 that are also members of S, note that 3 times 4 will give you a result that is 12, and 12 is not a member of S. Okay? So once it is possible, or once it is seen that two elements chosen at random from the non-empty set gives you a result that is not a member of the non-empty set, it means that the set is not closed. No matter the number of combinations that satisfy the condition, provided there is one combination or more that did not satisfy that condition, that set is not closed. So what will our conclusion be in this case? Our conclusion will be S is not closed with respect to multiplication. And why is that so? Because we've been able to choose two elements at random and combine them, showing that those two elements, the combination gives a result that is not a member of X. Okay? Now, let's quickly move to this other part. And let's take another example, still on closure. Okay? So remember, as a student, if you want to test the closure property, all you have to do is just to select two elements at random, any two elements at all, at random from the non-empty set in question, and check whether the combination using the binary operation will give you a result in that set. If it does give you, for all combinations, a result in that set, then the set is closed. If it gives you, for one combination or more, elements that are not in that set, then the set is not closed. Okay? So, let's test again. Now, as another example, or a part B to the first example 1 I took earlier on. Let's see. Given the set n of all natural numbers is n closed with respect to addition. Question mark. So now the set of all natural numbers is a set that contains elements ranging from 1 to positive infinity. In some cases, the set of all natural numbers can actually begin with 0. Okay? Let's assume that we are looking at a set of all natural numbers that begins with 0 in this case. If you begin your n, the set of all natural numbers with 0, and it ranges 0, 1, 2 to positive infinity. Now the question here is to check whether or not addition is, as a binary operation defined on n, makes n to be closed. So is n closed with respect to addition? The question is simple. So all we have to do, like I told you earlier on, is to select two elements at random. Now I'm going to select 0 and 1 that are members of n. So if 0 and 1 being members of n are chosen from n and combined under addition, 0 plus 1 will give you 1, and 1 is a member of n. Okay? Now, if you do the same routine, let's see a repetition of this routine. Now, if you do that for two other elements, let's select any two elements at random again. Let's assume I'm selecting 17 and I'm selecting an element 25 that is a member of n. You will notice that by implication, 17 plus 25, this will give me 42. And 42 is also a member of n. Now, this simply means that n, provided any two elements chosen at random from the natural number system gives you a result in the natural number system, it means that n, the natural number system, is closed. But in reality, I must tell you, and I must state this emphatically, please take note as a student that the natural number system is always closed with respect to addition. Now, if you try doing this with the natural number system for multiplication, you will come to realize that you can actually deduce or make this conclusion. So I'm going to state my conclusions here, that n, the natural number system, is closed with respect to multiplication. N is not closed with respect to division. N is not closed with respect to subtraction. Now, these are statements I would want you to verify. Please verify these statements and drop a comment in the comment section below, okay? Now, I'm going to state reasons why these statements are made. N, the natural number system, is closed with respect to multiplication. Why is that so? Any two numbers you select from the natural number system would always give you a result in n. So look at it this way. For the examples I chose earlier on, select 0 and 1 from n and multiply them. That is, in this case, the binary operation is multiplication. Once you multiply 0 and 1, it will give you a result 0, and 0 is a member of the natural number system. If you select 17 and 3, it will also give you a result in product that is a member of the natural number system. If you select 4 and 2 and multiply both of them, it will give you a result in the natural number system. All the numbers selected at random, any two numbers selected at random from the natural number system and multiplied will give you a result in the natural number system. What conclusion would that give us? It tells you that the natural number system is closed with respect to multiplication. Now, if you go to the next statement I have made here, is the natural number system closed with respect to division? The answer is a big no. Natural number system is not closed with respect to division. Why? If you choose any two, it is possible to choose any two numbers at random and discover by division that the result is not a member of the natural number system. For instance, in the natural number system, all the numbers that should be there should be whole numbers, positive whole numbers particularly. But let's assume we choose 1 and 3 at random. If you choose 1 and 3 at random that are members of the natural number system and want to check if a combination of 1 and 3 using division gives you a result in the natural number system, you will discover that this is not true. Whereas 1 and 3 are members of n, 1 divided by 3 will give you 1 over 3, and 1 over 3 is not a member of the natural number system, because in the natural number system there are no fractions. Okay, so once it is possible to see any two combination of elements that will give you results that are not in the natural number system, then it means that the natural number system is not closed. And the same thing is applicable to n not being closed with respect to subtraction. If you pick 1 and 3 that are members of n, check out this result 1 minus 3. 1 minus 3 will give you a result minus 2, and minus 2 is not a member of n. In the natural number system, there are no negative integers, and minus 2 is a negative integer even when we had used 1 and 3 selected from n. Okay, so all it takes for a number or a set to be closed with respect to a binary operation is that that set must have two elements drawn from it and combined with the natural combined with the binary operation, giving us a result in the set itself. Okay, now for more information on this property, please check out my videos on the natural number system. I have made videos on the natural number system, the real number system. I have videos on integers. I have videos all in my channel. So you go over those videos and you will understand this better. Let us quickly go to the next property on binary operations I would want to explain, and that is the property of commutativity. Okay, so let us quickly go to commutativity, and I'm going to say something very important here. Before we discuss the property of commutativity, please take note of something very important. Commutative property. Now, we are going to start with explaining why a binary operation is commutative. Remember, it is a binary operation that has to be commutative, not the set in this case. So a set is not commutative. Take note, it is a binary operation that has to be what? Commutative. So when is a binary operation commutative is the question we want to answer under this property. But before we do that, I'm going to explain something very important. Please take note of one thing. Under commutative property, unlike closure property, what I'm going to be doing here will be more detailed than what I discussed previously. So I'm going to start with the property itself. A binary operation asterisk defined on a closed set S or a closed non-empty set. A binary operation asterisk defined on a closed non-empty set S is said to be commutative if and only if A for any A, B element selected from S, A asterisk B is equal to B asterisk A. Okay? So, what is the property saying? If it is possible to select any two elements from a non-empty set S, a non-empty set that is already closed, and that is what I want to tell you that is very important. Before you define the commutative property of a binary operation on a non-empty set, that set must be closed. So you cannot start talking about commutative property on a set that is not closed. The set must first of all be closed before you can actually talk about a commutative property on the set for the binary operation. Okay? So when is a binary operation commutative? My statement in this property is a binary operation. So I'm going to put this here. A binary operation asterisk defined on a closed non-empty set is said to be commutative if and only if for any two elements A and B selected from S, A asterisk B is equal to B asterisk A. Let me quickly explain this before we take an example and end this video. Now, if you select A and B and combine it with the binary operation, the result gives you the same result as combining B and A, that is taking it in the other way around. Okay, the other way around. Then that particular property of commutativity exists on the binary operation. So all you have to do is combine in one order, combine in the other order, and then check if the results are equal. If the results are equal, the binary operation is commutative. If the results are not equal, then the binary operation is not commutative. Let us take an example and round up this video. So let's see. Now, for an example, given that a non-empty set S is the set of all real numbers. So I'm using the non-empty set S to represent the set of all real numbers. And remember, if you watch my videos on real numbers, you will know that real numbers can be integers, they can be natural numbers, they can be negative integers, they can be rational numbers or irrational numbers. So I'm calling my non-empty set S the set of all real numbers. Okay? So given that a non-empty set is the set of all real numbers, okay? Show whether or not the binary operation asterisk on S defined by A asterisk B equals A over B minus 2 is commutative. So let us use this example to check whether the binary operation asterisk defined on S, the set of all real numbers, is commutative. Now, for us to do that, this is what we are going to do. Now, we've been told that A asterisk B is equal to A over B minus 2. What it means, I like telling students that what this means is that first asterisk second is first over second minus 2. Interpret it as first asterisk second equals first element over second element minus 2. Now, what I'm expecting you to do, what I'll be expecting the student to do in this case, I'll be expecting the student to do this. If you want to solve that problem, all you have to do in this case is this. Now, state the condition necessary for asterisk to be commutative. Now, I'm going to do this. If asterisk is commutative on S, then A asterisk B will be equal to B asterisk A for all A and B that are members of S. Now, but what have we been given A asterisk B to be? We've been given A asterisk B to be equal to A over B minus 2. And how did I tell you to interpret this? A asterisk B is equal to first asterisk second, which is the same thing as first over second minus 2. Now, what if your first becomes B and your second becomes A? What would the result be? By that same interpretation, it will become first, which is now B, over second, which is now A, minus 2. Comparing both results would make you know whether the binary operation was commutative or not. So let's see. The question to ask ourselves now is A asterisk B equal to B asterisk A? Is that true? Now, what is A asterisk B? A asterisk B is equal to A over B minus 2. What is B asterisk A? B asterisk A is equal to B over A minus 2. Clearly, A asterisk B is not equal to B asterisk A. And what does that imply for the binary operation? This implies that asterisk is not commutative. Okay? So, to show that a binary operation is commutative or not, all you have to do is compare one order of arrangement or one order of combination with the reverse order of combination. If the results are the same, then the binary operation is commutative. If it is not, it is not commutative. Now, having said that, smash a like on the video. Make sure you subscribe to the channel. If you want more explanation on this, then drop a comment in the comment section and I'll see you in my next video.